Good afternoon, NDC London. You going all right? Yeah? Okay. I'm always so thrilled to take the NDC stage. I have been doing this speaking thing for a little while now, and I can say hands down that NDC is actually one of the best that there is. So let's have a quick round of applause for the organisers. Yes. Excellent. So as you would expect from NDC, we have had a pretty amazing start to the conference, right? Now, what did you think of Damo's keynote this morning? Were you all here early enough? Yeah? I thought it was quite timely. It's certainly something that I think about a lot these days, what our work days will look like as we continue to work with non-deterministic systems. And did anyone just catch Joe Mini's talk about usability testing? Someone saw that? Excellent. So, a few of you, so with me rounding it out, congratulations, you've hit the Aussie trifecta for today. You have won a prize worth absolutely £0, but it also comes with bragging rights also worth £0. So, you're welcome. So my name is Adele Carpenter and I'm a software engineer at Trifork Amsterdam, where I work on projects for the educational sector. So yes, Amsterdam, the Netherlands. I immigrated about 9 years ago, and it appears that, yep, this wonderfully refined accent is here to stay. So who here identifies as a C# developer? Yeah, a lot of you. That's exactly what I expected. Now, as a Java developer, excellent, yes, don't be shy. It's okay to be in the minority. I mean, it could be worse. We could be Haskell developers, or worse, COBOL developers, or even worse, vibe coders. Now, I must say that as someone that does attend a lot of Microsoft-centric conferences, I do feel a little bit like an outcast as a Java developer sometimes. Like almost embarrassed to admit the things that I have to do to keep food on the table, which is hilarious to me because if you spend enough time in both worlds, it's painfully obvious that we're all basically the same. You know, we shouldn't be fighting, we should be uniting against our common enemy, those that believe that JavaScript belongs on the server. And that's the mission of this talk today, is to bridge the Java and the C factions just a little bit and to have some fun in the process. So this is a talk concept I have been mulling over for a little while since I first started speaking in 2021. Now, has anyone seen this movie, which came out in 1999? Excellent, we've got a very emphatic hand at the back there. So, excellent. So this is the year that we got the just-in-time compiler and the collections framework as part of Java 1.2. So this is 10 Things I Hate About You, which is loosely based on Shakespeare's The Taming of the Shrew. And one of the core plot lines is basically heartthrob bad boy chases disinterested girl. And spoiler alert, girl does fall for boy, even though he's frustrating, annoying, and quite possibly the worst. Frustrating, annoying, and quite possibly the worst. Couldn't imagine why this inspired me to write a talk about Java. So, as is often the case with talk writing or any creative pursuit, really, you can have the idea but not the substance that's going to take it from fledgling to fully formed beast. Now, enter Mads Torgersen. So Mads is not a Java developer, at least not anymore. Now, for those that don't know, Mads is the lead designer of the C# language at Microsoft. So to C# devs, that makes him the king, and to Java devs, that makes him the enemy. So one of the cool things about being a speaker that generally gives more general talks is you get to speak for a lot of different communities, even if you aren't fully across the dynamics of those communities. And as an extension of that, you can end up having dinner with some pretty important strangers. So about this time last year, I found myself having dinner with Mads, and I'd been invited by our mutual friend Rendell, who's actually speaking in this room on Friday, so I do recommend you check out their session. Anyway, last year the three of us were speaking at the same conference and we were having dinner. Now, Rendell, a true polyglot developer, was relaying their experiences learning Zig and said something along the lines of, As fun as Zig and other new languages are, I just keep coming back to C#. There are just so many handy features that make it effortless for me to write good, performant code. And I naturally asked for an example, and Rendell offers up reified generics. What are reified generics? I naively exclaimed, although the speech bubble here on the slide is probably closer to what I said. So Mads, the lead designer of the C# language, who I had just met and made an excellent first impression on by asking who he was, patiently started explaining reified generics in C# to me. And when I asked what I thought was a natural follow-up question, what is the equivalent in Java, he then even more patiently explained that they don't exist in Java because Java has type erasure. And without skipping a beat, because he clearly knew who he was dealing with by this point, kindly explained what type erasure is. And this conversation encouraged me to go a layer deeper into language design and gave me the framework to explore what I felt regularly as a Java developer, namely frustrating confusion and Stockholm syndrome, in a much more targeted way. Now, at this point, I want to make clear what this talk is and what this talk is not, and who I am and who I am not. So I am a Java user. I spend most of my days building and maintaining Java and Kotlin applications in my role at Trifork. I am not an employee of Oracle, nor do I have any close ties with them. So any opinions I provide today are my own. And this talk? Well, this talk is a warts-and-all look at some of the features of Java that are the most frustrating, but at the same time, stay true to its overarching design philosophy. Build once, run anywhere, always and forever. And where it makes sense, I will compare Java's features and design choices with the equivalent ones in C#, which means that despite its title, this talk is actually more of a love letter to Java than an outright mudslinging. So if you've attended this talk looking for an hour of Java bashing, then you are sorely disappointed, and you are quite welcome to out yourself by leaving the room. And I'll wait. Now, I often get asked what my brand is as a speaker, and until I started writing this talk, I didn't really have a good answer, and I probably still don't, but if there's anything that I try to do above all else, it's to provide context. So why are we here doing what we're doing? Do we have to do these things this way? Are other industries or communities facing similar problems? And if so, what can we learn from them? So in the spirit of context, let's go back to the decade that arguably defined our entire industry as we know it, the 1990s. So it's 1991, and Sun Microsystems has just formed the Green Team, led by James Gosling. Note that Green Team, not Yellow Team, not Red Team, Green Team. So James is this one here. Now, in the backdrop of an exploding consumer electronics market, the team has started developing a small, reliable, portable, distributed, real-time operating platform. And what started as a C++ project has rapidly evolved into something else. It quickly became clear that C++ was an inappropriate choice, and a lot of the problems that the team were facing could be most easily resolved by creating an entirely new language platform. And by 1992, Gosling and the team had a working prototype running Java, at that time called Oak, on this device here called the Star 7. And it was complete with an animated touchscreen and Java's soon-to-be iconic symbol, Duke, so this one here. And after a few failed attempts to get into the electronics market, Sun pivoted into embracing the World Wide Web. So you see, this was the time before JavaScript, and this is what I imagine the world looked like before JavaScript anyway. And what Java offered with its platform-agnostic implementation in this magical time and place was a way to safely run code coming from the internet right there in the user's browser, turning the static web into the dynamic web. So Java 1.0 and the Hot Java browser launched in 1995, and the tech world, to put it mildly, went batshit insane. Time magazine named it in its top 10 products of 1995, declaring it a kind of Esperanto of the internet. The first Java 1 conference, held in 1996, drew in 6,000 attendees and made bold predictions for the future, like your desktop as you know it goes away and becomes the internet. You can recreate your home computing environment at a kiosk at the airport. And my personal favourite, software is never out of date. Of course, all with the big caveat, once the network is fast enough. And to say adoption of Java was quick is an understatement. By the end of 1997, Java was running on 80 million desktops, and the flourishing Java developer community was estimated at about 500,000 strong. Now, 500,000 doesn't sound like a lot, but that's about 20% of all developers on the planet at the time, and that is a conservative estimate. And this adoption was at least partly fueled by a deliberate design choice of Gosling and Co., which was that the new language should be simple, object-orientated, and familiar. Simple, really. How do we write hello world in Java 1 again? And if we, compare it to Python? Although, look, the fair comparison is probably with C++. And I suppose if we do compare these two examples, the Java code is a little bit simpler, right? It's a bit more explicit. But it's important to understand that when the designers of Java said simple and familiar, they are acknowledging that the expected early adopters of Java would be already familiar with C and C++, and that the learning curve for those developers should be relatively flat. Gosling and the team further focused on keeping what worked in C and C++ and leaving what didn't in the context of what was at the time modern object-oriented programming. So I suppose if I gave this talk 25 years ago, the title could be C++ sucks, so Java didn't have to. Now, in addition to simple, object-oriented, and familiar, there were 4 more guiding principles of Java 1.0, from which now on I'm just going to refer to as Java 1. But before I do that, I want to introduce you quickly to Smalltalk, Mesa, Seda, and Xerox PARC. And no, these aren't 90s aggro tech bands that your kids have just discovered and that your neighbours are complaining about. Smalltalk, Mesa, and Seda are programming languages that were developed at the Xerox Palo Alto Research Center, or Xerox PARC for short. And yes, when I say Xerox, I mean the company that brought us this. The photocopier, of course, not the woman. So Xerox PARC was established in 1970 to explore cutting-edge computer science and electronics to support Xerox's future tech strategies. It was supposed to take Xerox beyond photocopiers, and technically it did. So this is the Xerox Alto, one of the first personal computers, and it carried a bunch of innovations such as a graphical user interface, a mouse, and Ethernet networking. Computing urban legend actually has it that Jobs and the Apple team were inspired to develop the Macintosh after a visit to and a demo at Xerox PARC, which, given that we're in 2026 and Apple is one of the largest companies in the world and Xerox, well, isn't, could carry an ounce of truth. Anyway, this talk isn't about Microsoft or Apple. All this to say, though, that Xerox PARC heavily influenced modern computing as we know it, and that includes Java and C#. So, for example, Smalltalk, which was developed in the 1970s, was one of the earliest and purest object-oriented languages. In addition to IFL and Objective-C, it really put object-oriented principles at the heart of Java. Mesa was the second language to come out of Xerox PARC, and its main contributions to Java were structured exception handling, concurrency constructs, and portable bytecode-like execution. The third language from Xerox PARC, CEDA, is a systems programming language built on top of Mesa in the early 1980s. Now, as a language, its primary influences on Java were automatic garbage collection, modularity, and type safety. But the really cool thing about CEDA was that it came with an integrated development environment, including a compiler and a debugger. And this heavily inspired the tool suite that shipped with Java 1 and has absolutely shaped the way that we continue to work as developers in 2026. So, on to our second design principle of Java 1 now. Java should be robust and secure. One of Java's most notable moves was to step away from manual memory management, as done in C and C++, and towards automatic garbage collection. This contributed to the robustness of Java by reducing memory leaks and the presence of dangling pointers. And it was a huge innovation, and it became the approach for a lot of languages that followed, including C#. Now, as I just mentioned, Java didn't invent, but merely borrowed the concepts of automatic garbage collection from CEDA and Smalltalk. Java made it better, though, through innovations such as generational and stop-the-world garbage collection, along with heap segmentation, safe points, and write barriers, all of which were adopted in early versions of C#, although not always implemented in the same way. Strong compile time and runtime type checking also helped to prevent errors in programs written in Java. These features were inspired by CEDA and Mesa. Security in Java got a boost by its introduction of the sandbox model, which restricted untrusted applets from performing potentially dangerous operations such as I/O or network access on the user's system. And in addition, a bytecode verifier ensured that the bytecode did not violate Java's safety constraints before it was executed. Design goal 3, Java should be architecture neutral and portable. Now, the biggest wins here were compiling the code written by the developer to Java bytecode and the Java virtual machine specification, or the JVM spec. So with these two features in place, the code that the developer writes is compiled to a platform-neutral bytecode, which is then executed on the JVM, or by the JVM. And each operating system had its own implementation of the JVM that adheres to the JVM spec. And this provides for a consistent runtime environment across operating systems. This approach was adopted by C# with the Microsoft Intermediate Language and the Common Language Runtime. Portability was less of a concern, though, for early versions of C#, given the focus on the Windows platform, but we did see cross-platform capabilities improve from .NET 5. Design goal 4, Java should be highly performant. The Java bytecode instruction set was designed to be compact and efficient for interpretation. Java 1 also laid the foundation for the just-in-time, or the JIT compiler. And a JIT compiler is an optimization that converts bytecode into native machine code at runtime. So while the JIT compiler was not included in Java 1, the design gave space for future implementations to support just-in-time compilation. On the flip side, C#1 did ship with a full implementation of the just-in-time compiler, which meant that C#1 was in fact faster than Java 1's interpreter-based JVM, you know, when C#1 launched 6 years after Java 1. Design goal 5, Java should be interpreted, threaded, and dynamic. So Java 1 introduced multi-threading that just worked with the building blocks of the thread class and synchronization. So like automatic garbage collection, this was a pretty innovative feature for the time. And given the focus of Sun on the World Wide Web, multi-threading allowed it a high degree of interactivity for the end user, as the language supported many concurrent threads of activity. And the threading model Gosling and co chose was based on that of Cedar and Mesa. Now, one last thing to add is that while the Java compiler is strict in its compile time static checking, the language and runtime are dynamic in their linking stages. So classes are linked only as needed, which means that classes can be loaded dynamically at runtime via the class loader, allowing the system to adapt and extend itself without recompilation. C# supports a similar functionality, albeit through a different means, using reflection, assemblies, and optional dynamic typing rather than a built-in class loader system. But despite this different approach, though, the result and the underlying philosophy are essentially the same or very similar. So let's put those 5 design goals up again. So what do you think? Do these seem like reasonable goals? Yeah. Do you think the Java team succeeded in meeting these goals? Yeah. No? There's always one. Goal except number 4. Wow, skill issue. So, do you think that these are still relevant today? Yeah. So if these goals are so good and the team did so well in meeting them, then why do at least a third of you have Java-related hates coursing through your veins? Because to me, this seems kind of silly when we consider that C#1's design goals were met by looking like Java. And engineering is all about hard decisions and trade-offs. And it's completely reasonable to believe that the Java development team made some wrong ones over the years. You know, in some cases, at least. So let's start with the decision that, in my experience, gets the most impassioned response from C# developers. I'm speaking, of course, about type erasure. Now, if we're going to get so emotional, then we should at least understand what we're getting so emotional about. So what are reified generics and type erasure, and why do they matter? So first, just a quick refresher on generic types, which I think is most easily done through a code example. So in Java, we can declare a simple class box, which holds one value of any type in it, denoted by T. And so we declare the private field value and a constructor that takes that single value to create an instance. And then and the fact that value can be of any type is what makes the box generic. Then within that box class, we define 2 simple methods. There they are. Sorry, my apologies. And so one simply just prints the value field and the other prints the type of the value field. And here we just have the simple body of those 2 methods. And I really don't know what's happened here, because I seem to have mixed up my slides. This is actually the C# example. I really, I mean, these languages are clearly just so different. I mean, how could I have done this? So different. So I know I've just committed several heinous crimes here in this C# example. I mean, I'm using camel case instead of Pascal, and that is just the beginning. But this isn't just terrible theatre, and it is terrible, so thanks for sticking with me. But this code actually does compile and run. And before I show you, because I know that you do not believe me, let's take a closer look at box generic written in the elegant Java way. Because defining it like this means we only need to declare one box class. We don't need to declare a different one for each type, so integer box, string box, etc. So you can see in the demo class that we have the defined type of box to create an instance called intBox, which takes a value of 42, and stringbox, which takes a value of hello. So even in this trivial example, I hope you can see the power in this generic construct. Generics allow us to write type-safe and reusable code that works with different data types without us having to specify a concrete data type up front. Now, what about reified generics? Well, reified generics is a type system that makes the generic type information available at runtime. So if we take a quick look at the demo here, we can see the box file and the demo file with the run method. And then if we run it, the console prints out the type of each box with the values printed after that. And yeah, we showed that our Java-fied C# code actually does compile and run. Now, if we take a closer look at the real Java example, we can expect that print value works fine, but in the print type method, the call to value get class is lying to us. Now, why the trickery? The fact is that at runtime on the JVM, we just don't know what sort of box, int box, and string box are. So if we do an equality check, int box get class is equal to string box get class because the type information has been erased during compilation. And what this means is that at runtime, all generic types are treated as raw types such as object. You can't access the actual type parameter simply because it doesn't exist. But don't worry, the compiler's got you covered because if you do try to do an instance of check, for example, you will get a useful compile time error. I mean, that's just as useful as knowing the actual type at runtime, right? And so in practice, this means things like Jackson, or basically any library that deserializes data into Java objects, needs to work around type erasure by passing in the expected type as an extra parameter. And so you get something like this in the example here with a type reference. Now, why did Java do it like this? I mean, was it hubris? Ain't nobody gonna need introspection? Or was the Java team just lazy? The best, yet very unsatisfying answer that I can give you is deadlines and requirements. I know, I just heard all of your eyes collectively roll, but that is essentially what happened. So two key players in the early development of Java were James Gosling and Bill Joy. So James on the left here led the Java development team at Sun and is often referred to as the father of Java. And Bill is the co-founder of Sun and at that time was the CTO. Bill is also the creator of the VI text editor, which he developed in the 1970s. So James and Bill often had very different opinions about the key features of Java and would famously argue at length about implementation and design decisions. And one of the things they couldn't agree on was the implementation of generics in Java 1. Because while Bill fought for the inclusion of generics in Java 1, James is quoted as saying, "As a sort of design principle for something lots of people were going to use, I'd rather keep the whole with a label on it than do something I know is wrong." So with the time to launch Java 1 closing and the two men unable to agree, Java launched without several key features that Bill wanted, one of which was generics. And I think it's best summed up with this quote from a Green Team member, and the we in this quote includes Gosling. "We were right about needing to finish the language even though it had missing features. There was only about a 3-month window in which the whole Java phenomenon could have happened. We barely made it. But Bill was absolutely right about what Java needs long term." And one of the victims of this Esperanto of the internet phenomenon was generics, because by the time that the team were in a position to add generics in Java 1.5, a lot of Java code already existed in the world, and the Java team needed to stay true on their word of backwards compatibility. And I say needed here very deliberately, and the reason is because of the way the Java language evolves. Now, what do I mean by that? Well, the Java language has always evolved in consultation with the community. So Gosling admitted in a 2015 interview that before Java's public release, he could make a major, potentially breaking change to the language in as little as 10 minutes. No harm, no foul. But once there was a community around Java, real people writing real applications, he knew that it was necessary to involve the community in those decisions. Because in his words, if you make the wrong one, people could get very upset. So the Java Community Process, or JCP, was developed and implemented before Java's 3rd birthday. And as it turns out, adding generics was one of the earliest proposed extensions to go through the JCP. Here is the proposal here. So Java Specification Request 14, or JSR 14, was one of 3 potential approaches to solving the casting and runtime safety issues caused by a lack of generics, and it was the one supported by Gosling and Sun. So without any changes to the JVM spec, type erasure, as detailed in JSR 14, allowed code written before and after generics to be compiled to the same executable bytecode. So a method in a class compiled using Java 1.4 could still be called by a class compiled in Java 1.5, and the desire for this level of compatibility and stability is a core philosophy of Java. Gosling admitted at the time that no VM changes does mean that certain things become impossible, like runtime introspection, and in retrospect, he probably played down the importance of introspection on developer joy and ergonomics, for example. But given the fact that the year was 1999 and Gosling had his object-orientated hat planted firmly on his head, maybe he could be forgiven for taking this position. But why was no VM changes so important in the first place? Well, at this phase in Java's evolution, multiple vendors were already providing VM implementations. So in the words of Brian Goetz, the Java language architect at Oracle, getting a dozen JVM vendors to agree on if and how type information would be reified at runtime was a highly questionable proposition. But independent of Gosling and Goetz and VM implementations, at the end of the day, it was the community that signed off on type erasure in Java. Now, is that victim blaming? I don't know. But what I can say is that at the given time, with the given amount of Java code in the world and the given importance on backwards compatibility by the given community, generics with type erasure was the choice. And as for C#, well, the language designers over there made the opposite choice. They decided to update their VM and invalidate their existing libraries and all the user code that depended upon it. Sure, the old code just worked, as the CLR allowed pre- and post-generic code to run side by side, another design choice. However, it was still necessary to recompile the existing code in order to obtain full generic support. So, for example, if your generic supported code called a library that hadn't been recompiled, then it was your responsibility to manually cast to the expected type when dealing with that library. And that was a much more palatable option for the C# team than it was for the Java team, simply because there was comparatively little C# code in the world at the time. Additionally, and most importantly, there was no need to reach consensus with over a dozen VM implementation vendors. So adding a generics to the CLR was a decision that Microsoft and Microsoft alone could make. And I definitely believe that they made the right one. Reified generics in C# are a thing of beauty, and they are wonderfully engineered. They're also a wonderful example of the second mover advantage and the benefit of having a single corporate overlord. Now, I've been pretty compassionate and understanding of the Java language designers so far, but a girl has limits, and my limit is checked exceptions. So let me show you what I mean. So here are the signatures of two methods that each throw a checked exception, and if you call either method, the compiler will check that it has been handled explicitly at some point in the call chain. And this contrasts with C# and every other major programming language, which seem to cope just fine with exclusively unchecked exceptions. Now, we're going to try to do something that's pretty common in a production system. We're going to fetch some data for a list of users, process it, and then return the result. But since I work in the education domain, instead of a list of users, I'm going to make it a list of students, or a set of students' IDs rather, since we're dealing with unique values. And we want to find how many students from our set are currently enrolled in local schools. Now, in this example, the school name is actually the most reliable way to do this. So first we fetch the school name for a particular student, then we pass the return string into a known school using a custom parser. Then we filter the schools that are inside the local district and then count the number of elements in the resulting collection. Now, since we're iterating over a collection, we can use Java's streaming API. You know, it should be relatively clean and straightforward, right? Like this, we can even make use of method references using the double colon notation there. And of course, you could use a simple map rather than chaining, but I just like it to be super explicit. Now, the fetch requires an I/O operation, so it could throw a checked I/O exception, and because your colleagues are particularly conscientious, the pass school name method throws a custom checked school pass exception. So this is all wonderful, job done. Except you can't throw a checked exception from a Lambda in Java Streaming API, so you are forced to handle the exception inside of it. And if you take a little bit of a naive approach and simply do the bare minimum to keep the compiler happy, then you're going to have to wrap the offending methods in a try-catch, and you're going to end up with this monstrosity. Now, I don't want to be too hateful because part of me does understand what checked exceptions are trying to do. The intended use case of checked exceptions has always been for situations when you know up front what could go wrong, but we don't expect it to go wrong all the time. And the philosophy behind them is that the code that is calling the thing that might fail is going to have the best chance of knowing how to handle the exception. It has the context of what it is trying to do. Now, in the words of James Gosling, in Java, you can ignore exceptions, but you have to willfully do it. You can't accidentally say, I don't care. You have to explicitly say, I don't care. And given James's background working in operating systems, embedded systems, and VMs, this strong opinion on handling failures gracefully up front does make sense. But in a world full of closures and distributed systems and distributed data processing, it makes less sense. And the fact that Java is the only mainstream language that has checked exceptions is very telling. And we can compare Gosling's statement with one made by Anders Hallsberg when he was the chief architect of C#. Now here, Anders is giving the example of a UI, but this quote really demonstrates their differing philosophies on exception handling. You don't want a program where in 100 different places you handle exceptions and pop up error dialogues. That's just terrible. The exception handling should be centralized, and you should just protect yourself as the exceptions propagate out to the handler. Java developers have been complaining about checked exceptions for almost as long as Java has existed, but unfortunately, it doesn't look like they're going anywhere if we go by this comment snippet from Brian Goetz. So what do we Java developers do? Well, we don't need to do anything crazy like switch to using Kotlin or C#, both of which only have unchecked exceptions, because Java offers us the most elegant of very elegant workarounds. I'm speaking, of course, about the functional interface, which was launched as part of Project Lambda in Java 8. So a functional interface has exactly one abstract method, and is the closest thing you get in Java to a function that you can pass as a parameter. Meanwhile, C# has had delegates since 2005, but I digress. So we can use this construct to define an interface and then provide a default implementation for its one and only method. And once we have that defined, we then wrap our methods that throw the checked exceptions in a try-catch and rethrow as an unchecked runtime exception. This means we don't have to handle the exceptions in our Lambda logic, which brings us closer to what we would see in C#. And it's a thing of beauty, right? Right. But if we take a look at the actual C# example, I have to admit the language of select where count give me much better vibes than map, filter, and count as well. So link reads like it's for humans. Java reads like it's for computers. Well, not just computers, but giant computer nerds. And there's no chunky boilerplate hidden in some utils package either. We've got so much more room for activities. And in Java, there's this kind of prevailing tolerance for creating boilerplate and dumping it in a utils package where we can, in the context of what we have and in the conventions that Java developers have adopted. It's not so bad. I mean, once it's written and it's got unit tests, you can largely forget about it, but it's still code that you have to maintain, and it feels a little bit like cleaning your room by just shoving everything under the bed. And our tolerance for these language shortcomings as Java users is part of the problem. So the success of libraries like Lombok and previously Guava, they really highlight that. The fact that these libraries exist at all is honestly quite embarrassing and amounts to what I would call a code language smell. Still, it could be worse. We dump boilerplate like checked wrappers and other helpers like object mappers in utils packages, but at least we're not putting our business logic in automapper mappings. So I wanted to wrap up this talk with a discussion of the most controversial decisions of late and their associated fallouts. And I've picked two that stand out to me. But of course, if you want 100 opinions, ask 10 developers a question. So this is just my take, and I'm not speaking for anyone other than myself. So Virtual Threads was launched with Java 1 in 2023 and promised us faster applications with only minimal code changes. I mean, that sounds great, right? And while it might seem like it at first, it's not witchcraft either. You can think of virtual threads kind of like multitasking, not in the way that pop culture describes it by actually doing two things at once, but by the way it actually works, which is rapidly switching our attention between a number of tasks at once. That 2 or 3 seconds we look up from our phone to look at the TV and then back again. So virtual threads do a similar thing to scrolling TikTok, watching TV, and talking to our partner about their day, only much, much faster. Virtual threads allow an OS thread to be utilized while it is waiting for a blocking operation such as I/O to complete. And the improvement in throughput is then possible as the typical server application consists of a large number of concurrent tasks that spend much of their time waiting. And for the most part, virtual threads in Java 21 did deliver on the promise of better resource utilization, except for the cases where it didn't. So virtual threading came with a number of gotchas that even surprised Oracle, and the biggest one was thread pinning. So when code running on a virtual thread enters a synchronized block, the virtual thread is then pinned to the underlying platform thread, and it cannot do any other work. And if many threads all try to enter synchronized blocks and get pinned, then there aren't enough platform threads free, the system can deadlock, basically where everything is waiting and nothing is running. So here is a pretty telling graphic from the Netflix blog that I showed on the previous slide. You don't need to understand the specifics to get the message here. But here we have a web server throughput shown by the blue line, and then it suddenly drops to 0, and we see a number of sockets in the closed wait state by the brown line increase steadily. And this has to do with the way that Tomcat creates virtual threads with each request. Now, Oracle are many things, but they are certainly not stupid. So they did foresee pinning as a potential issue. But what they did not foresee was the practical impact of pinning, not only on the Tomcat case, but in cases where even seemingly simple production systems would grind to a halt. And this was especially a problem for applications that relied on legacy third-party libraries that made liberal use of synchronized blocks. And the breadth and somewhat unpredictable nature of deadlocking from pinning made Java users cautious about adopting the feature, and the Oracle team were quick, Java quick, to rectify this by allowing synchronization without pinning in Java 24, 18 months later. Yet, even if we subscribe to Java time, where 18 months or 3 release cycles is quick, I'm sure we can all agree that 10 years is a long time. I mean, 10 years is 1/3 of Java's 30-year existence. But that's exactly how long we've been waiting for Project Valhalla, which I think is summed up really well by this YouTube comment. I hope so too, David. I really hope so too. I think David's really captured here what it truly means to be a Java developer, to be waiting for the present and sometimes even the past to arrive at some point in the future. Project Valhalla was announced with much optimism in 2014. It even has a battle cry, codes like a class, works like an int. So what does that mean in reality? It means that we need to step back in time again. So I spoke already at length about how Java was developed in the early 90s to meet the demands of the fledgling World Wide Web and how that shaped the development of the language. And just like any other software project, faced pressure to launch and to be one of the first to surf the internet wave. Now, at that time, a memory fetch cost about the same in terms of compute as arithmetic operations. So Gosling and co, heavily influenced by Smalltalk, fully subscribed to the mantra that everything is an object. And this made sense. You know, object-oriented programming was the paradigm du jour, and rightly so. It brought with it significant benefits over the more common imperative styles, such as modularity, abstraction, and reuse. But Java also had to be fast. And so the compromise that was reached was that everything the user can define is an object. So alongside user-definable reference types would be 8 primitives: Boolean, byte, char, short, long, int, float, and double. So if your data didn't fit a primitive type, you modeled it as an object. And that was great, super flexible. The trade-off, though, was really clear. I mean, even simple value-suited types, like a point is just a simple XY coordinate, carried the overhead of heap allocation, an object header, a layer of indirection, an identity. But today, on modern hardware, the limitation isn't usually the size of the memory available, it's the performance hit of memory layout and indirection. Every pointer you chase costs cycles, and every cache miss sets you back. So Project Valhalla aims to give Java developers the well overdue tools to opt out of identity to achieve flatter and denser data layouts. So by flat, we mean cache efficient, fewer indirections. And by dense, we mean memory efficient. So data that belongs together is together. And the expected consequence of more cache and memory efficient code is a significant boost in performance. Now, how do you think that they're doing that? Keeping in mind that they've been working on this for 10 years. And they're doing it by introducing something really cutting edge, something Java developers have never seen before. Wait for it. Value types. How exciting. The past has finally arrived. I mean, even Brian Goetz had this to say at the JVM Language Summit in 2024. We've been working on this for 10 years, which is kind of appalling. And if you watch the video, you can actually see the embarrassment in his face. Now, think back, though, to a time when you've had a stakeholder say to you, why is this taking so long? Like, what was your response to that? Did you try to explain the technical constraints maybe? It's certainly been my reflex. And it's a reflex because that's usually what happened. You not had to build the thing. You had to clean up the mess of the past before you could even start to think about building the thing. And perhaps if you're really conscientious, you wanted the thing that you built to feel natural to the user, like it had always been there. And that's Valhalla. Java's epic refactor. So in that same talk from Brian, he said the first 8 years were actually spent on running experiments and building prototypes, basically deciding on the implementation, unraveling 20 years of technical debt, because this epic refactor actually goes to the center of Java's type system. Valhalla not only delivers value types, it also delivers null-restricted and nullable types, as well as primitive boxing, as outlined by these 4 Java enhancement proposals, or JEPs. So we have JEP 401, value classes and objects. This is available as an experimental feature. We have JEP 402, enhanced primitive boxing. It's technically in preview, but it depends upon null-restricted value class types, which is still in JEP draft stage. And lastly, null-restricted and nullable types, which is also still in JEP draft stage. So in all practicality, after 11 years, Java users are still waiting to tuck into the meat and potatoes of Project Valhalla. That said, the real work in Valhalla has been healing the rift between primitives and objects in Java's type system. And the bulk of that work has now largely been done to address the technical debt that has been holding Java back from fully embracing a more modern, data-driven and functional programming paradigm. A debt that grew larger when we got generics, as you can't generify a primitive, and a debt that grew larger still when we got lambdas, since the implementation of lambdas relies heavily on generics. So, for example, instead of defining a simple function of input type T and output type R, or predicate of type T in the streaming API as you can for reference types, for primitives, we actually need a highly specialized suite of functions. These ones here are just the ones for int. The same ones exist for double and also for long. So the ambitious sub-goal is basically being a more ergonomic and cohesive type system. Oh yeah, and the ability to handle all types, primitive value and reference, generically. Welcome to 2005. So, does Java still actually suck? I must admit, in writing this talk, I have at times felt a little bit like the wife of a deadbeat husband, like a little bit along the lines of, oh, you know, he had a really tough upbringing and he's really started making an effort. He's got a job stocking shelves now and he only plays video games 6 hours a day. Perhaps that's like a little harsh or maybe a lot harsh, but feelings are feelings and it's okay to have them. But I must say that writing this talk has exceeded my expectations in reigniting my love for Java. It's amazing what a little bit of effort in understanding something before you judge it can actually do. So yes, I still wish that Java had reified generics, and yes, I curse out checked exceptions on the daily, and yes, I still hate navigating my way through boilerplate because of course we have IDEs and LLMs generating our boilerplate for us now, and yes, I find the streaming API clunky and annoying, and yes, I still get surprised by auto-boxing and unboxing, and yes, Project Valhalla took too long. And I haven't even mentioned some of the more annoying tooling, like the build tool Gradle and the object relational mapper Hibernate. You know, not to throw too much shade in their direction, they're just tricky beasts to understand. And if you work on projects that need to be built, deployed, and connected to a database, well, you're going to encounter these tools, and you're going to encounter the mistakes of colleagues past. Yet, no matter how much what you feel about these tools, they are examples of the healthy and mature ecosystem that surrounds Java. A programming language is just a software project like anything else. The fundamentals are still true. You make decisions with the information that you have at the time, and then time goes on and the information changes, and importantly, you change. The things that you think are important no longer are, and so instead of dying on hills, you choose your battles with more wisdom. Now, certainly if you're building a language and a runtime relied upon by millions of users for the integrity and performance of their software, then some decisions are going to naturally be a little bit more permanent and harder to unravel, and you spend more of your day formally proofing your solutions. But Java was 20 years old when Valhalla was announced. 20 years might have been a little bit too long to hold on to the mantra of everything is an object. And when you start on a project, you don't always know what will come out of it. Sun started with the Green project, which yielded 6 prototypes of the Star 7 PDA. Now, who had heard of the Star 7 before I started this talk? Yeah, one nerd, great. And who had heard of Java? All of you, right? So the fact remains that 30 years after its inception, Java is still running mission-critical systems all over the world, from financial institutions, insurance, e-commerce, telecommunications, healthcare, government, logistics, energy, utilities, and it runs on 1 million of Android devices, and the JVM supports dozens of languages to compile to Java bytecode, including my pet language, Kotlin. And yeah, it pays my mortgage, and it's afforded me the opportunity to speak all over the world. You can say the same for C#, that's fine. I mean, this isn't a case of either or. You know, there's room in the world for both. Let's not get so emotional about the best way to tell a computer what to do. My name's Adele, and thank you so much for your time.